It seems like such a simple thing. You breathe it in every day without thinking. Its power is harnessed to generate energy, and as a force of nature, it can become uncontrollable and destructive. Air also plays a major role in the flow of a water and wastewater pipeline, and it's by far one of the most misunderstood aspects of the water and wastewater industry. The presence of air in a pipeline and its impact on operations raises important questions for engineers and operators that haven't always been easily answered. Operational problems, especially those apparent at startup, including broken pumps, valves and pipe, as well as faulty instrumentation readings, are often blamed on inadequate thrust blocking, improper pipeline bedding, or other similar circumstances. In reality, many of these problems are not caused by improper installation of the line, but by failure to de-aerate the line. Properly de-aerating your pipeline will safeguard it from air-related problems. If this isn't accomplished or is done improperly, efficiency will suffer and the pipeline is at risk. Air in a pressurized operating pipeline comes from three primary sources. First, air comes from the line itself. A pipeline isn't really empty prior to startup, it's full of air. To entirely fill the pipeline with fluid, you need to eliminate that air. As the line fills with water, much of the air will be pushed downstream for release through faucets and other outlets, which still leaves a large amount that will become trapped at system high points. This occurs because air is lighter than water and will collect at the high points. This pocket of air will continue to grow as it's fed from other sources of air in the line. Another source is the water itself. Water contains roughly 2% air by volume. During system operation, the entrained air will continuously separate out of the water and accumulate at the system high points. This 2% of air has the potential to become massive. A 1,000-foot length of pipe could contain a pocket of air 20 feet long if all the air accumulated in one location. A 1-mile length of pipe could contain a 100-foot slug. This would be true regardless of the diameter of the pipe. The last source of air enters through mechanical equipment. This includes air being forced into the system by pumps, as well as air being drawn in through packing, valves, and other equipment under vacuum conditions. A pressurized pipeline will always contain air, and that amount can be substantial. Now that we've identified the air sources, let's look at the impact it has on the system. Two problems become apparent. The pocket of air accumulating at a high point can result in a line restriction. And like any restriction, the pocket of air increases head loss, extends pumping cycles, and increases energy consumption. The presence of air can also promote corrosion in the pipe and fittings. As air continues to accumulate at the system high points, the fluid's velocity increases as it is forced through a smaller and smaller opening. As the pocket of air grows, one of two things will occur. The first possibility is a total flow stoppage. If system dynamics are such that the air cannot be continuously removed by the increased fluid velocity and pushed downstream, the system can become airbound, leading to complete flow stoppage. As the pocket continues to accumulate air, a pressure drop higher than pump capacity can develop and stop all flow. The second and more likely occurrence is that the increased velocity will cause all or part of the air pocket to suddenly dislodge and be pushed downstream, leading to a high-pressure surge or water hammer. Serious damage to valves, fittings, gaskets, or even line breakage can occur. This is the most serious of the possible consequences of air being allowed to accumulate in system high points. Here's a sample pipeline with an air release valve at the high point. An air release valve, sometimes referred to as a small orifice valve, will continuously release accumulated air during system operation. As air from the pipeline enters the valve, it displaces the water, allowing the float to drop. The air is then released into the atmosphere through a small orifice. As the air is vented, it's replaced by water, raising the float and closing the valve orifice. As air accumulates, the valve will continue to cycle in this manner to remove collected air. You can see how the Type 316 stainless steel float fluctuates to allow air to be vented while the water is contained. An air release valve will continue to open, releasing air during system operation, because forces acting to open the valve are greater than forces acting to hold the valve closed. In the absence of water, the only force acting to hold the valve closed is the system's working pressure. This is multiplied by the total area of the valve's opening, or orifice, to atmosphere. The orifice of an air release valve is typically very small. A system operating at 150 psi with a 0.1-inch orifice will have 15 pounds of force acting to raise the float and close the valve orifice. The forces acting to open the valve are the weight of the valve float and the mechanical advantage provided by the float lever. The effective atmospheric pressure on the valve is minimal due to the size of the orifice. So a valve with a float weight of 1.6 pounds times the mechanical advantage provided by the lever of 10 pounds results in 16 pounds of force acting to lower the float and open the orifice. Because the force acting to open the valve at 16 pounds is greater than the force to close the valve at 15 pounds, the valve will open during system operation. Again, these forces are negated when water is present in the valve, raising the buoyant float and closing the valve orifice. If we close the shutoff valve mounted on the air release valve outlet, the orifice is no longer able to vent air. As a result, air collects at the high point and creates a restriction. This demonstrates the effects of air on system flow when air release valves aren't used. We've seen how an air release valve will vent air at system high points, but air release valves will not admit large quantities of air or allow air in for vacuum protection. For that, you need an air vacuum valve like the one shown here. Air vacuum valves, sometimes referred to as large orifice valves, are used to exhaust large quantities of air upon system startup, as well as allowing air to re-enter the line upon system shutdown or system failure. As water enters the valve, the float will rise, closing the discharge port. The valve will remain closed until system pressure drops to near 0 psi. It will not open and release any accumulation of air while the system is under pressure. A close-up shows the water entering the valve, raising the float into the resilient seat and closing the valve. The float and float stem are guided by a hexagonal float guide. This assures positive seating of the float and protects it from colliding against the interior of the valve. All Valmatic air valve floats are manufactured with heavy-duty Type 316 stainless steel, and all floats are guaranteed for the life of the valve. Air vacuum valves are available in sizes 1/2 inch through 20 inch and have inlets and outlets of the same diameter. Note that as the water recedes, the float stays in the closed position. The float remains in position due to the forces holding it against the seat. This is because forces acting to keep the valve closed are greater than the forces acting to open it. The force is determined by calculating the outlet area times system pressure, which in this case equals 314 pounds of force. The only force acting to open the valve is the weight of the float, which here is 1/2 pound. As a result, the valve will not open under system pressure. An important benefit of an air vacuum valve is its ability to provide pipeline vacuum protection. If a system failure or column separation occurs and a negative pressure develops, the valve will open, admitting air into the line and preventing vacuum conditions, which can lead to a possible pipeline collapse or intensified air-related surge. While air vacuum valves will exhaust large quantities of air upon startup, it should be remembered that they will not continuously release air during system operation. Air release and air vacuum valves each perform specific functions. Combination air valves are designed to perform both. Combination air valves are the most commonly used valves. They perform the functions of an air vacuum valve and air release valve. Shown here are an air vacuum valve and air release valve piped together to form a combination air valve. Notice that the air vacuum valve stays closed while the air release valve continues to function during system operation. Combination air valves are available in single body and dual body configurations. The single body configuration is more compact and economical. The dual body configuration provides 2 independent valves, allowing access to the air release valve while the air vacuum valve continues to protect the pipeline. The dual body valve also provides a much wider range of sizing options. There are a number of different types of air valves, including well service, anti-slam combination, vacuum breaker, and vacuum priming valves. Valmatic air valves like these and the others demonstrated here are widely used in water and wastewater applications throughout the world for ease of operation and maintenance. Valmatic air valves